Hello everyone, this video is for KTCE math problem whose employment year is 2024. KTCE stands for Korea Teacher Certificate Exam. Anyone who wants to work at middle school or high school in Korea is supposed to pass this exam. And personally, I think the math problem in KTCE are somehow it's a kind of deep and interesting in the level of college mathematics. So if you are interested in, please try this problem by yourself first. Okay, let me dive into this problem. This problem is number 8 of type A math problem, which is a linear algebra. Actually, to be more specifically, this is about its characteristic polynomial and its eigenvalue and eigenvectors. Okay, let me give you a first point. First point of this problem is eigenvalues. Eigenvalues and its characteristic polynomial of given n by n. Here the matrix A is real matrix 3 by 3, but in general we can think n by n matrix or in a complex field if you want of this matrix. This is a crucial point of the linear algebra because all the information about its eigenvalues and following its eigenvectors are contained in this polynomial, which is called characteristic polynomial. So eigenvalue, we say eigenvalue when it satisfies this equation for non-zero vector n by 1 matrix, n by 1 matrix or vector n by 1 matrix V here, and A is in general n by n matrix. If their multiplication A times vector V is nothing but constant time, say lambda, and itself V here. And then we say this lambda is eigenvalue of this matrix A, and this vector V is eigenvector of matrix A. So when some specific vector V is multiplied by this n by n matrix, and its result is like the scaling of this vector, because lambda is constant, usually it could be a complex number. So when I arrange this equation then I will have, let me move the left hand side to the right, and I will have lambda times its identity matrix minus A times vector V equals to 0. So here, as you can see, to make each form as a matrix here, I multiplied n by n identity matrix here. Otherwise, lambda is just constant and capital A is n by n matrix. They are not matched together for the addition operation. Okay. So the whole this matrix is n by n matrix, and when you multiply it by some non-zero n by 1 matrix, its result is 0. That means this n by n matrix lambda times I minus A is singular matrix. That means it is not invariable. So let me say it this way. So that means we have its determinant is 0, and its determinant is dependent, is a function of lambda. So we say determinant lambda times I minus A is a polynomial of variable lambda, and we say this polynomial as a characteristic polynomial of the matrix A. Okay, so let me wrap up the relationship between eigenvalues and its characteristic polynomial. So eigenvalues are zeros of this characteristic polynomial. In more general, P sub capital A of T, which is the same as determinant of T times identity matrix minus A. Okay, so it should be singular, and eigenvalues is a values such that T times identity matrix minus matrix A is singular, and then we have each following non-zero eigenvectors. Which satisfies A times V equals lambda times V, some scalar factor of V. Okay, so if I multiply this relationship to matrix A, since A minus 3 times I is singular, you can think that its whole minus sign, which is 3 times I minus A, is also singular. So that gives us 3. 3 is one of its eigenvalue. And for the case of 3 by 3 matrix, I forgot to mention the degree of each characteristic polynomial, and each degree is n, and it is monic polynomial. Monic means each leading coefficient is 1. So characteristic polynomial of n by n matrix in general is a degree n monic polynomial. So in this case 3 by 3 matrix, that means its characteristic polynomial is degree 3 polynomial. Okay, and one of its 0 is 3. And by the condition B, we have other complex eigenvalue, which is alpha. And since its polynomial of degree 3 cannot have only one complex 0, so it should have its conjugate as a 0 simultaneously. So that means those two are the other two eigenvalues of this matrix A. So for the matrix A, which is 3 by 3 real matrix, it has eigenvalues, 3 eigenvalues, 3 alpha and alpha its complex conjugate, and its following, let me say, eigenvectors are v1, v2, and v3, which is ordered set. Let's say ordered set. So v1 corresponds to 3, v2 corresponds to alpha, v3 corresponds to alpha bar, its complex conjugate. So for instance, A times v2 is alpha times scalar of v2, and A times v3 is alpha bar times v3, as it goes. Okay, let's go into our second point, which is a diagonalizable matrix. Usually, diagonal matrix let's say capital D is a matrix whose n by n matrix whose form is order 0 except the diagonal line. Only the entries in its main principal diagonal line cannot be 0, so all other entries are 0 except this principal diagonal line here. Actually, they also could be 0, but the only entries that could be non-zero are the entries on this main diagonal. Okay, let's just say main diagonal. Okay, so diagonal matrix is a matrix, let's just say diagonal matrix A, and is a matrix that makes our lives easier. So by multiplying some proper invertible matrix P, invertible n by n matrix, and P inverse on its left hand side, then we can get some diagonal matrix here. And then we say this matrix A is diagonalizable. So one caution is that invertible matrix does not guarantee it is diagonalizable. Diagonalizability is more stronger condition than invariability of a matrix, n by n matrix. Okay, so it's a caution. Please don't misunderstand that invariable matrix is diagonalizable. This is not true. Okay, this is only true when this n by n matrix has ordered basis consisting ordered basis of its eigen vectors. I'm sorry. Ordered basis. It has ordered basis consisting of its eigenvectors. So for instance, like the case of the matrix A on our problem here, it has three non-zero, it should be non-zero eigenvectors, and their corresponding eigenvalues are all distinct. That guarantees that those three eigenvectors are independent. So that means it could be a basis for, since it is real, it could be basis for R3, let's say. And to be more specifically, this invariable matrix P can be achieved by eigenvalues is positioned on its column vectors from v1, v2 to the n. So then you get the invariable matrix, which makes your matrix n by n matrix A can be converted into a diagonal matrix D. And in this case, its diagonal matrix is its main diagonal line. Its values from lambda 1 to lambda n, they are all eigenvalues of matrix A. Okay, so in this case, A times V sub I corresponds to lambda I times V sub I. So I goes from 1 to n here. If I say more rigorously here, okay. So what we have here, we can say that this matrix A is diagonalizable. So that means we have some invariable matrix P. So by multiplying P and P inverse on its right and left hand side respectively, we get diagonal matrix here. Since I ordered these eigenvectors v1, v2, and v3, and its corresponding eigenvectors will be 3, alpha, and alpha bar, and all the other entries are 0 here. Okay, so we have invariable matrix some invariable matrix P here. And we can go further that for the matrix B, by multiplying this invariable matrix P on both sides, P and P inverse, like this, and we have a square minus a plus 5 times I, and P inverse on both sides. And as you already know that when you multiply P inverse, and then we have a benefit on it. So a square is in the middle, then we can rewrite it a times a, and we can insert P inverse for each a. So this P inverse is nothing but identity matrix. So actually I did nothing, but by doing this I get those two diagonal matrix D times D, which is square of D. So let me call it this specific diagonal matrix as capital D. So by doing a calculation, we have D square minus D plus 5 times I, because you know when we multiply P inverse both sides on each identity matrix, and we still have identity matrix, which is 1 1 1, and all the other entries are 0 in this case of 3 by 3. Okay, and then by computation, you have 9 minus 3 plus 5, alpha square minus alpha plus 5, alpha bar is square minus alpha bar plus 5. This is our diagonalizable form of this matrix B here. The last point of this problem is a relationship between minimal polynomial of matrix A and its characteristic polynomial of A. So for instance, let me give you a simple example. When for the 2 by 2 case, if I have a matrix, real matrix 1 1 0 1, and my characteristic polynomial for this case t times I minus a, and its determinant, this will be determinant of t minus 1, and negative 1 and 0, and its determinant will be nothing but t minus 1 and its square. So the zeros of this characteristic polynomial is 1. We have only 1 0 for this characteristic polynomial whose degree is 2, because it's 2 by 2 case. And in this case, the minimal polynomial is a polynomial such that whose degree is the smallest polynomial, which contains all zeros of this characteristic polynomial P capital A of t here. So the polynomial whose degree is minimal is the smallest, let's say smallest degree, but still contains all the zeros of its eigenvalues. In this case, the minimal polynomial has degree 1. So obviously, which is less than the degree of its characteristic polynomial. So as you have observed, when we have repeated zeros of characteristic polynomial, then there's a gap between the degrees of its minimal polynomial and its characteristic polynomial. Unfortunately, in this case, for the condition C, there's a gap between the polynomial, between the degree of the minimal polynomial and degree of its characteristic polynomial. So that means the matrix capital B, let's say characteristic polynomial of this polynomial B, T has repeated zeros. Okay, that's our small conclusion that comes from condition C here. And then all the zeros of characteristic polynomial of matrix B is nothing but the diagonal entries of this diagonalized matrix. Okay, so in this case, the entry 1 and 1 is nothing but 11 here, real number. So and let me say those two entries are complex conjugate, so if we have diagonalized form of matrix capital B is like this, whose all the main entries of the main diagonal is 11, then in this case its characteristic polynomial will be t minus 11 and its cube. And then alpha should be real number, because alpha squared minus alpha plus 5 is 11, gives us two real roots. One is 3 and the other is minus 2, but this is not the case because alpha should be imaginary number, so this is not the case. So what we have for the other case is that those two eigenvalues should be the same, but they are different from 11. Not 11, but they should be the same. That's our second conclusion for this condition C. Okay, I'm not gonna do all the detailed calculation, but let me give you some taste of it. So since alpha is complex number, I can write it. Its norm is square root of 2 e to the I times theta here. And then for the square of alpha, we have 2 times e to the I times 2 theta here. Okay. And then we have a condition for those two, the last two entries, which are complex conjugate with each other, should be the same. So that means it should be real value. Okay. And then I can rewrite it as the 5s are cancelled out. Okay. And what I have is 2 times e to the I times 2 theta minus square root of 2, and it's e to the I theta should be the same as minus I times 2 theta minus square root of e to the minus I theta, because it is a complex conjugate. And then as you know, that e to the I theta is nothing but cosine theta plus I times sine theta here. For the case of square of alpha, it is the same. So cosine of 2 theta plus I times sine of 2 theta. Okay. And since its result is real, its imaginary part should be 0. So its imaginary part should be the same on both sides here. So let me derive only its imaginary part, which is 2 times sine of 2 theta minus square root of 2 sine of theta should be the same as 2 times sine of minus 2 theta minus square root of 2 sine of minus theta, and 2 minus signs gives us plus here. Okay, so if I move this term to the left and this term to the right, and I have 4 times sine of 2 theta equals to 2 times square root of 2 times sine of theta. And since sine of 2 theta is 2 times sine theta and cosine theta here. Okay. And as you can see, since alpha is imaginary, so it's imaginary, that means its imaginary part, which is sine of theta, should not be 0. So this sine of theta is not 0, so we can cancel them out, and what's left is 8 times cosine of theta should be 2 times square root of 2, and we get the following values. And sine of theta is nothing but square root of 1 minus square of cosine, and in this case 1 minus 2 over 16, you will get square root of 7 over 8. Okay, so you get the whole result for the value of eigenvalue alpha, which is square root of 2 times square root of 2 over 4 plus I times square root of 7 over 8. Okay, so you get the whole eigenvalue, which are 3 alpha and alpha bar. Okay, and the trace of matrix is sum of its eigenvalues. You can do it, and determinant is multiplication of all the eigenvalues. So 3 times norm of alpha and its square. So you can please do it by yourself. Okay, let me wrap up this problem. So on this problem, which is linear algebra, the problem is, is about diagonalizable matrix A. Okay, so diagonalizable matrix makes our life easier because we have this magical invariable matrix P, and we multiply it on both sides, P and P inverse, on its right and left hand side, and we get a diagonal matrix. And when we know that its specific form of eigenvalues, when eigenvalues are all distinct, it guarantees that we have ordered bases consisting of its eigenvectors. So this makes the matrix A is diagonalizable, and we get its specific form of diagonal matrix. And then rest of things, just you deal with this diagonal matrix. And then for any matrix which has polynomial form of matrix capital A, that also could be diagonalizable by multiplying this same invariable matrix P and P inverse on each both sides. This was the core of this problem. Okay, that's it. Thank you.